Origins events, staggering events. They have defined the cosmos and challenged our understanding. But perhaps the most challenging origin was on a small, insignificant world. A defining moment long ago for planet Earth.
I think there are a handful of great questions in science, and unquestionably, the origin of life is one of those. Our understanding of the origin of life and of the prospects for life elsewhere has changed dramatically in the last 10 or 20 years.
It may be that life is being carried by the interstellar and interplanetary winds, and the small bacteria are spread everywhere, and the universe is indeed teeming with life.
Today, many who search for the origin of life look for alien life. They look to the possibility that life on Earth fell from space. Not long ago, science was adamant that life on Earth originated on Earth. That biology's incredible tapestry, more than 500 million species, was entirely homegrown. Science believed that planet Earth was a rare crucible for the stuff from which life is made. But no longer.
Well, we see in space the basic chemistry of life. Carbon chemistry and organic chemistry is the chemistry of the universe. We look in the outer solar system, on the asteroids, on the moons of Jupiter, on the moons of Saturn, and we see organic material. Comets go racing by, and they are rich in organic material. The universe is full of organic material. The universe is full of water. Water and organic material. What more could one need for life?
NASA's Christopher McKay is one researcher whose thoughts have taken a heavenly turn. It's a difficult turn for any scientist to make, because looking to space for the origins of life was, until recently, an outrageous heresy.
The Earth is the center of biology. It is the standard of biology. Our complete understanding of life is based on our studies here on Earth. It could be that in time we will begin to appreciate life on Earth as just one member of a set of life forms throughout the galaxy. And Earth will not be then the measure of all things biological. And that's what I personally believe will happen.
Chandra Wickramasinghe is another true believer, another heretic. Chandra is the high priest of a theory called panspermia, a theory which proposes that microbes from space colonized our planet.
I took it upon myself to challenge and to question the conventional wisdom. There is no logic that demands that the origins of life are here on the Earth.
In the 1960s, the British astronomer turned his mind to the nebulae. Great molecular clouds stretching across light years of galactic space. Nebulae are windows to the distant past.
It's like a time machine. the whole history of our solar system written in the stars. You're seeing essentially the material from which stars are born.
30 years ago, it was thought that nebulae were chemical infants, comprised mostly of very simple molecules, those based on hydrogen and helium. Chandra proposed, and subsequently proved, that nebulae are rich in carbon-based molecules, the complex organic molecules from which life is made. Then Chandra asked an obvious question. Where did the complex organics scattered through interstellar space come from? Initially, he and collaborator Sir Fred Hoyle, another British astronomer, assumed that the origin of these molecules had nothing to do with biology, with the processes of life. But their data troubled them.
I wasn't satisfied. The agreement wasn't perfect, and there were assumptions to be made that I wasn't very happy about. What other process could be producing all this stuff? Molecules that were related to life in really vast quantities. Why not think about the possibility that biology was doing that?
Chandra and Hoyle looked once more to interstellar space, to radio emissions, optical observations, the infrared, readings which they couldn't explain. Molecules differ in their ability to absorb or reflect light. A measure of these differences is called the absorption spectrum. On the spectral chart, there was a strange bump. The signature of particles that were round, hollow, and organic.
I was getting almost frightened at the consequences that were emerging from my train of thoughts.
The astounding conclusion from Chandra and Hoyle that interstellar space contained a countless number of tiny life forms, that the cosmos was littered with frozen bacteria.
We found that bacteria have the right sizes to be the interstellar dust, and the only reason for not considering that was a purely sociological one, because people hadn't deemed it proper to think of life outside the Earth.
Science and heresy are old companions. 500 years ago, in Renaissance Poland, another astronomer questioned the conventional wisdom. His name was Nicholas Copernicus. In the 16th century, the Earth was believed to be the center of the cosmos. This idea was beyond question. It was virtually an article of faith. The genius of Nicholas Copernicus was to dethrone our world by proposing a cosmos with the sun at its center. The establishment was outraged. Although Copernicus escaped retribution, he died soon after his masterwork was published. Many who championed his ideas were hounded by a vengeful church. The Italian astronomer Galileo excommunicated. The Dominican monk Giordano Bruno burned at the stake.
How close can you zoom up on the...
We can go very close with this.
In proposing that spacefaring bacteria colonized our world, Chandra is trying to remove the Earth from the center of biology.
The telescope will now be moving to the object that we actually want to see on the screen.
Just as Copernicus removed it from the center of astronomy.
It's the dust and the solid particles that I've been mostly interested in. And
Chandra believes bacteria are in the dusty, gaseous material from which planets form, the material of the early Earth. He says that all life is descended from these microbes, that each of us has cosmic ancestry.
Okay, as you can see, the camera is now...
Chandra's ideas, like those of Copernicus, drew the wrath of the establishment. But this time, the outrage was from the science establishment.
intense hostility. They thought in the early 79, 80s that we had gone nuts.
20 years on, many are asking, was Chandra crazy or visionary? His beliefs are unchanged, but the course of the science mainstream is shifting.
Well, the biggest problem with the origin of life is that we don't have much data to constrain the ideas, the theories. So there's a range of theories that are being discussed right now, and they tend to go in and out of fashion. So we can look back and look at theories that life came from outer space and landed on the Earth, and for a while those were just dismissed as being science fiction. And yet now that idea is coming back into serious consideration.
Origins researchers are turning to space because demonstrating how life originated on Earth is proving more difficult than anyone imagined. To see why, we travel to the infant Earth, back to when life first appeared. Our time machine is the study of fossils, the traces which life forms leave in rocks. With the fossil record, we retreat through the corridors of evolution, through a catalog of ecosystems. The age of mammals, tuned by the pulse of Ice Age glaciers. The age of dinosaurs, of shallow seas and steaming forests. The explosion of life forms in the Cambrian Age, the first complex organisms. To the Precambrian and simple life, the long reign of the single cell. We used to think these earliest cellular life forms came into being when the Earth was middle-aged, about 2 billion years ago. This allowed an incredible length of time, the first 2.5 billion years of our planet's existence, for cells to evolve from their molecular components. But this slow, simmering recipe for life has been destroyed by recent fossil evidence. We've discovered that life was on Earth 4 billion years ago.
When the evidence for the first life form was only 2 billion years old, then one could imagine that life slowly percolated in a prebiotic soup for a few billion years before the first organism originated. But what's happened over the last 30 years or so is our understanding of the origin of life on Earth has been pushed back, further and further back.
Life's ancient ancestry means it had relatively little time to evolve. Life's ancient ancestry places it in the harshest of nurseries. 4 billion years ago, the Earth was being bombarded.
It's clear that life evolved not in a kind of quiet, peaceful pond, but in a violent, impact-ridden environment. It's hard to see how you could have had a beginning to life on Earth if you were evaporating the oceans from giant impacts.
To imagine the cataclysmic events of early Earth, scientists like Chris Chiba look to echoes in present-day space. To the thunder of comets and asteroids, the solar system's wanderers. In 1994, the fragmented comet Shoemaker-Levy 9 struck Jupiter, the solar system's largest planet.
There is an explosion that would make the explosion of a nuclear weapon seem tame. Something like 100 million megatons.
On Earth, craters bear witness to similar impacts, which today, fortunately, are rare. But in the early solar system, the cosmic traffic was much heavier.
We can imagine an impact rate that's thousands or millions of times higher than it is today. The primary evidence comes, interestingly, from the examination of the moon. When we look up at the night sky and we look at the surface of the moon and we see that heavily cratered surface on the lunar highlands, we are seeing events that are the end of the formation of the planets, what we call the late heavy bombardment, the last bits and pieces falling in on the planets.
Heavy bombardment of comets and asteroids of the early Earth didn't tail off until between 3.8 and 3.5 billion years ago. So life had to begin in the midst of this bombardment.
So that's gotten a lot of people thinking that, well, maybe life did not start on Earth from a prebiotic soup, but somehow was carried to Earth and arrived on Earth full-blown, like Athena from the head of Zeus, ready to go.
If cellular life came from space, from where in space? Chandra Wickramasinghe would have us believe that life came from the interstellar dust. But more recent converts to the theory of panspermia have another idea. They look to a place closer to home, one of our neighboring worlds. Their theory is called planetary panspermia, and at its heart is the planet Mars. Talk of space-traveling Martian microbes would have been ridiculed just 20 years ago. Not anymore.
It's starting to look like it really is possible to move microorganisms between, say, Mars and Earth. We don't know that yet, but it's looking more and more like that's possible.
Although planetary panspermia is a new concept, the possibility of life on Mars has tantalized us for more than a century. But in the late 1970s, that possibility was dealt a severe blow when the Viking missions arrived at the Red Planet to search for microorganisms. Viking unveiled a climatic nightmare. The planet's atmosphere, 100 times as thin as the atmosphere of the Earth. The average surface temperature, minus 63 degrees centigrade. Surface water, little or none. Surface life, not according to the instruments carried by Viking. To Christopher McKay, the brutality of Martian conditions can best be understood by comparing them to the worst the Earth has to offer.
Here in Death Valley, we see one of the most inhospitable places on Earth. Only about an inch of water a year. And yet this environment is paradise compared to what we find on Mars. In the air here, there's thousands of times more moisture than there is in the atmosphere of Mars. Here, at least, there's some life forms that can survive in those environments where water can be concentrated and trapped.
Life forms like bacterial algae, sheltered by the valley's salt pans. Hardy life forms, which the Martian environment would kill within moments. But Christopher is comparing Death Valley to Mars present. The test for planetary panspermia, the theory that life on Earth has Martian roots, is in the red planet's distant past.
Main engine start, 1, 0, and liftoff of the Delta rocket with Mars Pathfinder.
The rover deployed by the Pathfinder mission examined the chemistry of Martian soil and rock. Its instruments confirmed that Mars in its youth was a very different world, a much warmer world.
One of the most intriguing things about Mars is that Mars had flowing water on its surface at about the same time that life began on Earth. Life as we know it is utterly dependent on liquid water.
A large percentage of the Martian surface is a flat, featureless landscape. The Earth has similar topography, but it's hidden. Hidden by the oceans, whose floors are dominated by vast uniform regions we call the abyssal plains. Many think the lowlands of Mars were the floors of ancient oceans. Oceans which were consumed by a global climatic catastrophe.
Something went very wrong on Mars, and the planet freeze-dried. It's now a frozen desert. If there is no life on Mars now, it may well be that life went extinct after the planet froze and dried out.
Establishing that life was possible on early Mars is only the first challenge for planetary panspermia. For the Martian ancestry of life on Earth, timing is critical. Life had to evolve on the red planet before it had the opportunity to do so on our world.
I think we can make at least one argument that would argue that Mars was a better incubator for life than the Earth.
The jewel of that argument is in the night sky. The Earth's only natural satellite isn't the largest moon in the solar system, but no other comes as close to matching the size of its planetary parent. More than 4 billion years ago, our big moon had a traumatic birth.
There was, we believe, the moon-forming impact, where an object the size of Mars slams into the Earth. And literally knocks a big chunk of the Earth off into a ring around the Earth, which coalesces to form the moon. This would have been an absolutely devastating event in terms of any life or even any organic material that would have been on the Earth. And so Mars may have had a more benign early epoch. And during that early epoch, life could have slowly incubated on Mars, while conditions on Earth were still much too harsh in terms of the moon-forming event for life to have maintained itself.
The next challenge for planetary panspermia is transport. getting microbes from Mars to a young, lifeless Earth.
There are a number of steps in this process that a brave bacterium would have to survive in order to make the journey safely from Mars to Earth.
Those steps are being pursued in unlikely places. With an unlikely strategy for exploring space. Every year, up to 1,000 meteorites are collected from the ice fields of Antarctica, the Earth's frozen continent. Most are sent to the Meteorite Curatorial Facility at the Johnson Space Center in Houston. One specimen, found on the ice cap in 1984, was the rarest of meteorites, a piece of Mars.
Look at this weird texture here. Let me check this area.
Within this rock, a NASA-led team of scientists found something they scarcely believed.
I've never seen anything like that either.
Suddenly, when we came across this feature, we began to see something that really had the shape and morphology and size that could have been something like a microfossil. It literally stopped us in our track. And if life was represented by this form, we were seeing evidence of a past biology on another planet in our solar system. That particular night, I could not sleep.
On at least one issue, the NASA team can rest easy: the Martian origin of their now famous rock. It was confirmed when data collected by the Viking landers was matched to the contents of another Antarctic meteorite recovered from the ice fields in 1979.
This rock is from Mars because trapped inside it you see Mars' atmosphere. We went to Mars with Viking and measured the composition of the atmosphere and the surface rocks. And then one of my colleagues was studying this rock, and he discovered trapped inside little black glassy areas like you see on the surface here, gases that had the exact same composition.
To date, 13 meteorites with a Martian signature have been identified.
We are dealing with a group of samples from a unique reservoir in the solar system, and that reservoir turns out to be the planet Mars. And in any court of law, I think we now can say this is a proven case.
Although there's some interesting fibers in this as well.
Far from proved is the case for microfossils, the tiny shapes the scientists claim are the remains of ancient Martians.
Notice there's a little bit of aluminum there, too.
They stand by those claims, but concede their evidence is circumstantial and widely disputed.
Put in 100,000.
Those who suspect living Martians traveled to early Earth are following the controversy closely. But to them, of far greater interest is the vehicle in which the alleged microfossils traveled. Mars meteorites are the unlikely spaceships which make planetary panspermia possible.
If we didn't have the rock sitting here telling us that they'd gotten here, I think many of the theorists would conclude that it was impossible. But here they are, challenging us to understand how they got here. And what we think happens is an object like a comet or an asteroid will slam into the surface of, say, Mars, and most of the rocks it hits will just be vaporized. But some of the shock energy will go to literally accelerating pieces of material into space, without necessarily destroying the rock that it's accelerating, just carrying it up almost like on a wave.
Some small fraction of the ejecta that's blown off of Mars in a big impact is not strongly shock heated. The temperatures are low enough that bacteria could survive. And in those rocks, it might be possible for a bacteria to hitch a ride. The question then becomes, will they survive that journey?
Oh my goodness. You can see the entire continent of Australia from here. The whole thing.
The vacuum of space is a tough place to make a living, especially for complex oxygen-hungry organisms.
Yeah, I need to be up a foot now.
Without a pressurized suit, a human would be unconscious within seconds, dead within 1 or 2 minutes. We've discovered, however, that space holds far fewer terrors for single-celled organisms. Their fitness has been tested by marooning a colony of bacteria in Earth orbit for 6 years aboard a science platform called the Long Duration Exposure Facility.
And what was found was that if the bacteria could be protected against ultraviolet light from the sun, they could do just fine in the vacuum of space, and they could do just fine with the radiation they were receiving over those 6 years, apart from the ultraviolet light. If you're within a meteorite, you're shielded.
Other challenges for a brave Martian microbe are starvation and temperatures approaching absolute zero. Both are death sentences for complex organisms, but not for bacteria. Some species can enter a state of suspended animation by forming radiation-resistant spores. When times are tough, a spore-forming cell dehydrates. Then it builds a tough protein coat around its DNA to protect its genetic heritage. Spore formation is a microbe's version of hibernation, a far more effective version.
We're beginning to understand just how long bacteria, spore-forming bacteria in particular, can live in a dormant stage.
To a spore, spring is a fresh supply of water and nutrients, which triggers the resumption of metabolic activity. Spores have been revived, returning to the active phase of their life cycle after 3 million years of dormancy in the Antarctic ice sheet. They've also been found in the stomachs of ancient bees, recovered from amber, fossilized tree sap.
People are finding in the ambers bacteria spores that are still viable after 40 million years. And that's an incredible long period of time to remain in a dormant state. To go from planet to planet only requires 1 million years or less. So a meteorite coming from Mars, if it had inside it a spore in a dried out state, that could easily survive these long transit times.
The final hurdle for our brave Martian microbe is a fiery passage to the surface of early Earth. When a meteorite enters the atmosphere, it's heated by friction. Tiny meteorites are vaporized or heated to the core, hundreds of degrees centigrade, far too hot for any organism to survive.
It's the biggest one we've got. It's 110 kilograms.
But for slightly larger rocks, it's a case of hot on the outside, cool on the inside.
Lots of fusion crust, the dark covering where it melts as it goes through the atmosphere.
The exterior is charred, but the fusion crust shields the interior in the way the space shuttle is protected by the heat-resistant tiles on its underbelly. Temperatures within the meteorite are kept within the survival zone of a tiny astronaut.
If life originated on Mars first, there is a chance it could have been blasted here and gotten to Earth before life began on Earth, in which case we may have been colonized by Martian microbes.
Could this be our ancestral home, the source of life as we know it? The theory of life's Martian ancestry has taken great strides, moving from the ridiculous to the possible. But is it probable? For many researchers, like biochemist David Deamer, that's too great a step. Yet he and his colleagues still look to space. They look with different eyes, believing the heavens played a smaller role, but nonetheless a vital role, on the origin stage. David and many others hold fast to the belief that life on Earth emerged on Earth, from a soup of organic molecules at our planet's surface. They're trying to find a way for that to happen quickly, to match the timetable demanded by the Earth's most ancient fossils. A rapid, inevitable rise of life on a young, impact-ridden planet.
When we talk about the origin of life, we're trying to go back 4 billion years in time. So that means that we have to simplify. Looking to the sorts of molecules at the simplest level that are in today, and then try to work ourselves back into that early time, seeing how these could come together to organize themselves into the first living structures.
Simple is a misleading word for single-celled organisms because they rival the complexity of so-called higher life forms. The human body is built from 60 trillion cells, yet much of the human whole is mirrored by the interplay of organic molecules within a humble bacterium. Nucleic acid, DNA and RNA, is the cell's brain, directing activity and growth. Carbohydrates are the cell's energy source, and proteins its building material. Proteins are made to order within the cell from amino acids, often referred to as the building blocks of life. For those convinced that life originated on the infant Earth, a crucial first step in building their case is to identify a source of essential organic molecules. One solution is panspermia, a different theory of panspermia. That instead of microbes, space provided life's chemical ingredients. In the solar system, organic carbon is distributed unevenly. The inner regions are carbon poor.
Most of the environments that are rich in carbon in the planetary environments are in the outer solar system. In the inner solar system, the conditions are right in terms of temperature. The outer solar system has the ingredients. So it's a very attractive idea of some way to bring the right ingredients to the right place. And comets and asteroids represent one vehicle for doing that.
The idea of panspermia, was it a spore falling in from some previously existing life? Or, in my opinion, more likely, was it a set of carbon-containing molecules falling to the Earth's surface, getting caught up in the Earth's chemistry, and emerging then as an organized system that can reproduce itself?
On the one hand, a big comet collision is an extremely violent event. On the other hand, comets are rich in organic molecules. Maybe 20% of a typical comet is organics. So cometary organics, or also asteroidal organics, could have been a dominant source of organic molecules on the early Earth.
Space has provided the building materials, but what of the blueprint? The recipe for turning the bounty of heavenly organics, including the all-important amino acids, into the molecular machinery of the first cell.
There are hints of how to begin to string those amino acids together, to hook them together like boxcars to make a protein. But even getting to the point of early proteins on early Earth is something that is not well understood. And then the step from proteins or early nucleic acids, the sort of molecules that your DNA is made out of, the step from that to a full cell is an almost overwhelming kind of step.
David Deamer is trying to take that step. A step into the kitchen of creation. The attempt to make life in the laboratory. To date, he and all others have failed to do so, but David remains hopeful.
It will likely happen, in my opinion, it'll likely happen in our lifetimes, 10, 20, 30 years.
Many Origins researchers share David's optimism, but not all.
One way to explain life's rapid appearance on Earth is to say that it just occurs very quickly in an environment that has the suitable ingredients. And if that's the case, one would imagine that we'd be able to reproduce it in the laboratory. And it could be that the theories that we're pursuing and simulating in the laboratory are just completely wrong. And that accounts for our failure to duplicate in the laboratory what we see happened rapidly in nature.
We could be wrong about the origin of life because we don't really understand life. We've learned only recently how little we knew and how much more there is to know. Today, the science of biology is in revolution, a revolution from which an intriguing suggestion has emerged. That instead of originating at the surface of the Earth or any other world, life could have risen in the depths. The volcanic springs of New Zealand are home to billions of heat-loving microbes, hyperthermophiles.
85.3 degrees centigrade for a final temperature, so I think we should take a sample here.
25 years ago, the existence of these organisms was unsuspected because the way they make a living was considered an impossibility.
Let's see what we get from the core. Yeah.
Hyperthermophiles not only thrive at temperatures approaching and in some cases exceeding the boiling point of water, they do not need the energy provided by the sun. Instead of photosynthesis, they use chemosynthesis. Their metabolisms are powered by chemicals dissolved in the volcanic brew. In the late 70s, the first deep ocean hydrothermal communities were found. Strange ecosystems powered by volcanic vents. These communities are just the tip of what is being called biology's new frontier. The deep frontier.
There is a deep biosphere on the Earth. Microorganisms are being recovered from rocks as much as several miles down in the Earth's surface. It may be the case that the deep biosphere of microorganisms on Earth actually accounts for more biological mass than everything we're used to seeing with our eyes at the surface of the Earth. including all the mass of the forests. And that begins to change the way you think about life in this solar system or life in other solar systems, because it suggests that life doesn't have to be a surface phenomenon, that life may exist at depth on many other worlds.
The deep biosphere is rekindling hopes for Mars, which many thought had been dashed by Viking's failure to find life at the surface.
It may be that life evolved at the surface and has since retreated to deep niches as the surface froze and dried. In that case, life could still be there in deep aquifers on Mars, just as there is life in deep aquifers on the Earth. Then there's another important question, and the important question is, even if life can exist at depth, once it has originated, can life originate at depth, or can life only originate at the surface? If it turned out that life could originate underground, then many other places in the solar system become possible. Any place that you have liquid water at depth could be a site for life.
It's hard to imagine a way for organisms from the depths of a planet or moon to travel between worlds. But what if a large body wasn't necessary for the evolution of life? Some suggest that life may have originated in the hearts of asteroids and comets.
We think we need an environment in which the water and the organic material can mix. And one such container could be literally the inside of a comet, where radioactive heating early in the history of a comet could generate a molten liquid core. And so in the interior of the comet, in sort of an interesting zero-gravity environment, we could have droplets of water and grains of organic material reacting. Maybe this could be a site where life could incubate.
If life evolved in comets and asteroids when the solar system was young, if life was riding in comets and asteroids during the late heavy bombardment, then comets and asteroids may have seeded life on Earth. To panspermia's high priest, life in the solar system's wanderers is an old idea. Chandra Wickramasinghe has been writing about comets for 20 years. Chandra's version of panspermia relies on comets to sweep up frozen bacteria from the interstellar clouds and deliver it to planets.
We immediately connected not only the cosmic bacteria, the interstellar bacteria, with comets, we were then able to connect comets logically with life on Earth.
Chandra has spent 2 turbulent decades on panspermia's pulpit. The softly spoken astronomer is confident that his is an idea whose time has come.
I have not the slightest doubt that the trend would move inexorably in the direction of life from space.
Life from space, proved beyond reasonable doubt, would utterly change our concept of Earth's place in the universe. It would open a window to a cosmos teeming with life forms we would call alien, but with which we might have much in common.
If we entertain the prospect that life can easily move from planet to planet, then we have to start thinking of the galaxy the way we would think of islands in an ocean. But they may be isolated with respect to some of the life forms, some of the big lumbering life forms that can't go from ocean to ocean. But it means that the little guys, the ones that can move, are going to be the same everywhere. They're going to be widespread.
Establishing this island universe would do for biology what Nicholas Copernicus 500 years ago did for astronomy: remove the Earth from the center. It would answer the greatest questions, the most profound of questions.
We all want to know if we're alone. We all want to know if life is common or extremely rare. There's no end in sight to how much our knowledge of the origin of life and of the possibilities for life elsewhere is going to increase as we continue our exploration of the solar system. And as we begin to bring pieces back and examine them for their chemistry and for hints of life. We would begin to get a hint at how abundant life might be, not only in our own solar system, but throughout the cosmos. This is an adventure that's only just beginning.